Hi folks, I realised that I did not record the last session, so for those of you that missed it, I'm going to go through what we did, which will actually take less time. So, HNMR, so it's assumed that you are comfortable with carbon 13 NMR. Very important, that's what yesterday's task was all about, so that you could get very comfortable with it. What I'm going to do is I'm going to quickly go through the starting point. So see this test tube here, we've got our TMS, our solvent, our compound. This is the same for both HNMR and CNMR. I'll go through some exam paper questions that come up through this, and then after that I'm going to talk about the spec of HNMR. I'll go through a simple one at the start, and then I'll go through a bit more complex ones which will have these splitting patterns. So I suppose that's why HNMR may be considered at times a little bit more difficult, because there's a few more things to consider. So you should know about the number of peaks and environments and that association. You should be able to explain what chemical shift is. And then we've got two extra things here that need to be considered when we talk about HNMR. Going straight into it. So this is our starting point with HNMR. So we've got our organic compound, whether unknown or whatever it is. We have our reference compound here. You should know what that's called, and it's our tetramethylsilane, not saline, silane. And looking through exam papers during the last 10 or so years, a common question that tends to come up is to draw the structure of this tetramethylsilane. So you should know that it's a silicone in the middle, and then there is 4 methyl groups surrounding that, like so. You need to be able to draw this. If your knowledge is up to scratch, you actually could quickly deduce that you can actually draw this as a tetrahedral structure as well, because 4 bonds, etc. So if you can cross-curricular your knowledge there, or cross your topic knowledge, you should know you can actually draw this as a tetrahedral. Right, so what's also important is that you need to know the reason. So why do we use this molecule? Why is this molecule used? And the reasons you should know. And it's important actually to know all of the reasons that are mentioned in the spec and in the book. And the reason is because in the past they will give you 2. So they might give you 2 reasons. They might say that, okay, so TMS is very volatile and it's also inert. Name other reasons as to why TMS is used in NMR. Well, before I mention the reasons, it's important to note why is volatility important? Well, when something is volatile, it's sort of easily removed, because this compound can easily sort of become a vapor or turn into a gas. So if something potentially went wrong, this compound can be removed, which is good. Inert, we know that it means it does not react with the organic compound, so it won't affect the results. What other reasons could you put? Well, it's non-toxic, self-explanatory. You won't die or be, something very bad happen to you when you use it. Another good reason is so this has carbons and hydrogens, and the carbons and the hydrogens, depending on what they ask you, they might say HNMR, they might say CNMR, or they might say both. Well, the carbons and the hydrogens are in the same environment, or experience the same environment. And in turn, what that does, it produces a very strong peak. So when we throw this into the machine, it's unmistakable. It's really far to the right. Produces a very, very strong peak, and everything else then is sort of, if you remember, sort of downfield from that. So those are the reasons. I would advise you to know them all, because again, they can give you 1 or 2 or 3, and you sort of name the rest. So do remember that. Talking a little bit more about the solvents. So CDCl, it's exactly the same as for CNMR, but there's a few questions surrounding this. They'll ask you, why is this used? And why not something else like CHCl3? And they can also ask you other compounds that are used as a solvent in NMR. We'll start off with this. So it's a very, very short answer, but I'd like to explain exactly why. I'm sure you probably know anyway, because that was a requested that from me yesterday. But this, we know that this is HNMR, and HNMR will detect hydrogens in their environments. So if we use something like CHCl3, also known as chloroform, that lovely substance that makes people pass out, why don't we use this and we use this? And this D is an isotope. So you're not going to find this on the periodic table. It's an isotope of hydrogen. So D is known as deuterium. And so if I have normal hydrogen looks like this. And this hydrogen, or the deuterium, looks like this. So that's your deuterium there. And I suppose if you remember, when it comes to NMR, NMR will only detect hydrogens or carbons that have odd numbered nuclei, and your nuclei is your protons and neutrons, so your odd numbered nuclei. HNMR will detect the hydrogen, so it will detect the H from the chloroform, and it will just affect your results. Whereas deuterium has an even number of nuclei, so it's not going to, I won't say, it's not correct to say that it doesn't get detected. It does to a small degree, but what you would answer to that particular question is why that is used is that it does not affect the results. So that's it, long story short. It essentially doesn't affect the results, whereas the chloroform would. The deuterated chloroform won't. Again, they might ask, okay, so deuterated chloroform is used in NMR. What other solvents can be used? There are a few. A very common one is tetrachloromethane. So again, this is not used. So this and this are common solvents used. The reason why this is used is that it doesn't affect the results. This is used, obviously it just doesn't contain any hydrogens, so it's going to work well. Won't affect the results, and because it doesn't have hydrogen, so that's that. Okay, now I'm going to show you, we're just going to power through examples. So I'm going to show you a very simple low resolution spec of a HNMR. So when you come across exam questions with HNMR and their specs, they're not going to come up as single peaks like this, but we're going to start off this way just to ease ourselves in. And it's important that you can identify hydrogen environments and that you can couple them with the peaks that you're given as well. So we're just going to use these sort of single peaks to do that. So it's important, well, we know that the number of peaks is the number of environments. So we know that there's going to be 2 hydrogen environments somewhere in our ethanol. It's important to remember the chemical shift will tell us the exact environment. And this new thing here, this new word, integration, essentially it tells us the number of hydrogens in the environment, even more so as a ratio, but I'm just going to say that they're the number of hydrogens in the environment for the time being, just to apply to this. So can we identify hydrogen environments? Well, there's 2 of them in ethanol, or methanol. Sorry, this is methanol. And so when you come across a hydrogen in an OH group, it's quite an exception, which will make sense when I talk a bit about it a little bit more with the other specs. But this is always going to be an environment by itself. So that's one environment right there. Another environment is going to be how many? So remember, it's not 3, 1, 2, 3. If you think about it, we're not concerned with the carbons. We're trying to figure out how many hydrogen environments there are. So this hydrogen experiences the same environment as this hydrogen, and it experiences the same environment as this hydrogen because they're all bonded to 1 carbon. They experience the same environment. NMR machine will pick that up. So these are considered one environment. It's sort of a rule of thumb. You know, how the hydrogens bonded to the one carbon is going to be equivalent to one environment, but that's one way to look at it. So how do I know which hydrogen environment is which peak? Well, when I talk about integration numbers, these little numbers on the top, now usually they're in ratio form. Simplicity reasons, I'm just going to use it as the number of hydrogens. This long peak here is telling me that the hydrogens in this, or the hydrogen environment here, has 3 hydrogens in it. Therefore, it must be this methyl here. This, on the other hand, this peak is telling me that the hydrogen environment producing this peak has 1 hydrogen in it. So obviously it has to be this one. Now it's important to also remember chemical shift. So the more electronegative, so this is an electronegative oxygen here. So the hydrogen environment, similar to the carbon environments we dealt with, the hydrogen environment that is closer to an electronegative, or the hydrogen environment closer to an electronegative element, is going to have their chemical shift further to the left. So if you remember, the analogy I used before was that the oxygen was like perfume. It sprayed perfume, and the hydrogen environment that was closest to it would be affected the most. So if you remember, these hydrogens are essentially de-shielded. Just put de-shielded by this oxygen. So the more de-shielded they are, which means the closer they are, the more shift they get to the right, the more chemical shift they experience. Again, even though this hydrogen and this oxygen is actually, yeah, again, it's close to the oxygen, it's shifted over here. Funnily enough, this doesn't really experience much, I suppose it doesn't experience a lot of effect from this oxygen regarding it being de-shielded. However, you don't need to know this, but this oxygen actually blocks off the effect of these protons from this hydrogen. So they're not neighbours of it or anything like that. Again, it'll make more sense down the line. But just to note, this is an environment by itself, and these 3, because they're bonded to the same thing, are in the same environment. This goes to 3, this goes to 1. Now, looking at this element, it looks complicated. If I was you, I would pause it and try and name it. So very quickly, I look for the parent chain, and the parent chain is 1, 2, 3, 4. Is there any functional groups? Yes, so there's 4 carbons, it's going to be some kind of a bute. I see there's a alcohol group here, it's going to be a butanol, some sort of butanol. And I've got these 2 alkyl groups, 2 methyl groups on the carbon. I would number them, the priority would be numbered from right to left, because my priority functional group is here, and it's just easier then, therefore, to name it from left to right, because it's close to this. So on the 3rd carbon, I have 2 methyl groups on a butanol. So it's 3,3 dimethyl butan-1-ol, or butanol is fine there, but 3,3 dimethyl butanol. So what are the carbon environments, or the hydrogen environments? Again, OH, this is going to be environment all by itself. And I've got a hydrogen environment here, another hydrogen environment here. When I look at this, I see a lot of clusters going on. And again, remember, looking at this carbon, this carbon is not bonded to any hydrogens whatsoever. It is, however, bonded to these sort of 3 methyl groups in a way, and they've got hydrogens onto it. So an NMR machine will not detect carbon. It will, however, detect the hydrogen environment. So looking at the methyl groups are bonded to this carbon. So this hydrogen is bonded to this carbon, same as these, same as these, same as these. All of these hydrogens are experiencing the same environment. So all of this is one let's do that a bit neater. All of that is considered one environment. I can just see if I can do that somewhere. One hydrogen environment, and I've got a carbon there, but one hydrogen. So I've got 4 hydrogen environments, 4 peaks. It seems fairly accurate. Now, which peak belongs to which environment? Well, I'm going to look at my integration number. And I should say here, not all questions are going to give you an integration number. I'm just doing examples where there is an integration number. But anyway, this peak has 1 in it. This is telling me the hydrogen environment that produces this peak has 1 hydrogen, which has to be this guy over here. Now the next one, it's telling me that there are 2 hydrogen environments that are producing, there are 2 hydrogen environments that have 2 hydrogens in them. So if I look at my molecule, I know that my 2 hydrogen environments are these 2 CH2s here. They're the only ones with 2 hydrogens in their environment. How do I know which one goes to which peak? So again, remembering the electronegativity, remembering that the environment which is closer to an electronegative element will be more affected by that. It'll be shifted more, it'll be de-shielded more, therefore it'll be shifted more to the right of the chemical shift. It would experience a bigger chemical shift. So in this case, this green group CH2 is going to be shifted more to the right because it's closer to the electronegative element. So like that has to be this one. This group, however, is going to be the next one. So again, it's not as affected by the influence of this electronegative oxygen. And then last but not least, 9 hydrogens, it's going to have to be process of elimination. This belongs to this peak. And again, I am going to say it's important to note that integration numbers really is, I suppose, the ratios of it. But for the time being, this is perfectly fine. We can say that this represents the amount of hydrogens in that environment. Because when we talk about integration, we talk about the area below, the area below the peak. And that's proportional to the number of hydrogens, and they're numbered here. So I'll just go with that for now. So that's one example. We're going to go to a little bit more complex one now. So this is the kind of spec that you're going to come across when you look at any of the questions. So we see here that this is a spec for ethanol. So we throw ethanol into the machine and this is what comes out the other end. And it's nicely color coded. It's a nice little transition to whatever these guys are about. These are what's called our splitting patterns. So splitting patterns tells us how many protons are adjacent to the environment in question, i.e. how many hydrogens are neighboring the environment we're looking at. So that'll make a little bit more sense. So I'm just going to take the blue one. So I'll take the CH3. So this hydrogen environment here is over here. And if I look, it has 1, 2, 3 of these sort of splitting patterns. And that tells us how many protons or hydrogens are adjacent to this environment. So if I just circle it here, do it in pink. So this environment, we look at the peak, or look at the splitting pattern here. And to look at the splitting pattern, that's what tells us what's adjacent to it. So what's adjacent to this is this CH2. And how many hydrogens or protons are adjacent? 1, 2. But when I look at the actual splitting pattern, there's 3 sort of mini peaks or little splitting patterns. There's 3 of them, yet there's 2 protons. So what does that mean? Well, there's a rule called the N+1 rule. And I've got a little table down here that will illustrate that as well. So whatever the amount of protons that are adjacent to the environment you're looking at, you just add 1 to it. So in this case, we have 2 protons, N+1, so it's 3. And that's why we've got 3 little splitting patterns. And there's a name on 3 splitting patterns, and that's called, we call this type of a splitting pattern a triplet. Oh, excuse my writing. So I have a little table here that'll explain that. So it's very important not to get confused with the splitting pattern and what that means, and the chemical shift and what that means. So again, the shift or the chemical shift tells us what environment the H's are in. The splitting pattern tells us what hydrogens are adjacent to that environment we're talking about. So again, there was 2. So protons, there is 2 of them. Again, the n+1 rule. So 2 + 1 is 3. We call it a triplet. And here's just another little appearance of the peak and what that looks like. So we see that there's 3 splits, and that's what's represented by this also, 1, 2, 3 splits. So I'm going to look at, that's that environment. I want to look at the CH2 now and what that means. So the CH2 environment is over here. So this is my environment. We see that there's 1, 2, 3, 4 splitting patterns. And where does that come about? Well, that tells us the protons that are adjacent to it. So I've got 1, 2, 3. So I've got 3 protons. There's the n+1 rule, which means it's going to be 4. And that's called a quartet. And that's why there's 4 splitting patterns there. So again, looking at the environment, the splitting pattern tells us the amount of protons adjacent to it, and you'd use the n+1 rule. So we had 3 protons beside it, n+1 makes it a quartet, and there's another way you can look at it as well. Just 1, 2, 3, 4, 1, 2, 3, 4. I'm going to look at this OH now, and it's really important to note here about this OH is OHs will always, always, always be a singlet. So singlet is what's represented by this 1 high peak here, singlet. Always be singlet. And the reason is because, remember I mentioned earlier that this hydrogen, when we talk about the patterns or the splitting patterns and that they're the amount of protons adjacent to it, well, when it comes to the H and the OH, there are no adjacent hydrogens or protons. Because again, you don't need to know the reason, but it is because I think oxygen produces this sort of a shielding on it. So these protons don't have any influence on this H. So when the NMR picks it up, it comes up as just the 1. So the 1 environment, because the splitting patterns, again, it basically says there's no adjacent or neighboring hydrogens. So if you think about it this way then, so we know that the OH has no protons beside it, but then there's the n+1 rule, and that's going to equal 1, hence our singlet. And you can see that down here as well. So again, there's no adjacent hydrogens. n+1 is going to be singlet, and that's why there's a little bit of a spike here, and OH will always be a singlet. Very important. And that's kind of all I need to know there. I'm going to do another problem again, and it's really trying to, it'll take a while for you to get used to it, but just please distinguish between what a chemical shift means and what the splitting pattern means. So going down here. Oh yeah, and before I go on, in the AQA, so I see I've got a doublet as well, just highlight them all. So AQA, there's loads of types of splitting patterns. If you can think of one that has like 7, it'll be a septet, or 6 will be like a hexet. But AQA, you only need to know doublet to quartet. But I find that they do incorporate the singlet a lot. So, I mean, this came out straight out of an AQA exam, so I don't know why it's beyond me why they don't say that in the spec. But the reality is you need to know it. Singlet, quartet only. Cool. Right, so here's another example. So again, the first thing you should do, so this is a ester. It is ethyl ethanoate, and this is the spec for ethyl ethanoate. So the first thing you should do is you should identify the hydrogen environments. So pause the video if I were you, and I would try and identify the hydrogen environments. So I'm going to go from left to right. I have a hydrogen environment here. I have a hydrogen environment here. And I have a hydrogen environment here. Okay, so 3 environments equal 3 peaks. So I have, let's try to figure out, so which hydrogen environment is coupled with which peak. So I would have a look at, let's have a look at this CH3, the pink one. And again, the splitting patterns will help us figure out which environment belongs to which peak. So again, we need to figure out how many protons are adjacent to this environment. So if we have a look around, there's actually no hydrogens that are adjacent to this hydrogen environment. Because if we look at it, the environment this is experiencing is that the hydrogens are bonded to a carbon, and this carbon is bonded to the C, double bond O, single bond O. There is no adjacent hydrogens. So none, but then there's the n+1 rule. So it's going to be the singlet. And the singlet is this bad boy over here. Okay, it has that one splitting pattern. Okay, so we figured out that one. Now looking at this, CH2, the green, we need to, again, looking at the environment, but trying to search for how many protons are adjacent to it. So we look at the CH3 over here, and we see that there's 1, 2, 3 hydrogens adjacent to this environment here. So again, the n+1 rule, and that's going to equal 4, which is known as the quartet. So it's kind of hard to see here, but this small one here is 1, 2, 3, 4. This is the quartet. So we know that this carbon environment is producing this peak over here. And last but not least, I know it's process of elimination, but it's good to go through it. We look at CH3. We know that we need to figure out, okay, so how many splitting patterns will it produce? How many protons are beside it? 2. 2, n+1 rule, plus 1 is 3, so it's going to be a triplet, and lo and behold, there we go. Cool. So that's good, we can kind of figure that out. So splitting patterns are good for helping us find out which environment goes where. What you can always think about is when you think about chemical shift and the environments that they're in, if we take a look at the one that's furthest away, so we know the one that's furthest away or furthest shifted to the right, it sort of experiences the most effect on the electronegativity or the electronegative atom. So we can see that this environment here, the CH2, is actually right next to an oxygen. It's bonded to an oxygen. So this oxygen is going to de-shield these hydrogens. Therefore, it's going to push them furthest to the right. And out of all the the environments, this green group is going to be most affected by that, hence why it's shoved over here. If we take a look at the next one, so we see that the hydrogens here aren't really, I know the way we can see that there's a double bond O here, but they're not really affected. They're not bonded, I suppose, beside an oxygen, or they're not bonded to a carbon that's beside an oxygen. Their environment is a carbon that's attached to another carbon. So again, relatively, they do experience some de-shielding, but not as much as the green group, okay? And then last but not least, the one that's least affected, so we've got the CH3 group over here, it's furthest away from both these oxygens. It's not going to be de-shielded or very little de-shielding, so it's going to be very near to the right on that. Okay, and another one I wanted to go through. Okay. So looking here, this is another ester, and this is methyl propanoate, and this is the spec it produces when we pop it through a machine. And what I have down here is a more aesthetically pleasing version of the data you'll find in the data booklet. So you'll have a separate one for CNMR, and you'll have another one for HNMR, and that's the one for HNMR, and it's just outlined in a different way. Okay, so first of all, the first thing we're going to do is looking at this. There's a few ways to go about it, but I always think it's good to identify the hydrogen environments. So I can see that there's one here. You can pause the video, do it yourself. There's one here. There's a hydrogen environment here. And there's a hydrogen environment over here. And with this question, we're going to sort of apply using and identifying certain groups using this sort of data sheet over here. But first of all, how will we match up? So which hydrogen environment belongs to which peak? So again, I'm going to take this one that's furthest to the left. This is the environment. It's like a CH3. And the hydrogen environment, so how many protons are beside that? I'll just do this in pink. So again, I've got two. There are two hydrogens that are adjacent to the environment in question. So 2 n+1 rule, it's going to be the triplet. So there's only one triplet, so this group is going to belong to C, okay? The next one, looking at this environment, we look at the protons that are adjacent to it, which are the ones from over here. So I've got 1, 2, 3, 3, n+1. It's going to be 4, which is a quartet. And again, the quartet is over here. So we know that the CH2, the H's in that environment produce the B peak. And then I look at the furthest one then, and I see that it's, so this environment here actually experiences there's no protons, I suppose, that are adjacent to this, because the hydrogens involved in this environment are bonded to a carbon, it's bonded to an oxygen, it's bonded to COO. There are no other hydrogens. So it's none plus 1 is going to be the singlet, I should say. So that one belongs to A. Excellent. So when we're trying to associate, looking at the chemical shift and the environments that they're in, and these environments will give us a lot of insight into what kind of functional groups that make it up. So if I take C, for example, so I know that this group, or this hydrogen environment is producing this peak. And if I look at the figures at the bottom, I can see that it's in around the 1. And that's actually producing, so if we go around the 1, yeah, so that's actually producing a CH group over here. So this is, let's see if I can, this is an R CH. So we've got all this, and it just gives us an insight as to what it might be. Now, if I look at the next peak over here, I can see that, okay, it's produced by this environment. And if I look at the figure, so it's in around, what, 2.34-ish. So if I go down here, I can see that I've got an N attached to a CH, a double bond CO, CCH, and an argon to a CH. Well, it's actually, so I can see here that this is the group that it's telling me that what this signal means. So it's actually the double bond CCH, double bond O, CCH. That's what this is here, it matches up perfectly. And the last but not least then, if I look at my singlet, and I know it's produced by this hydrogen environment, if I look at the figures, I can see it's about, what, 3.6-ish or so. So I go down, I have a look. And again, it's this CHO. So it's about, 4 to 5. Yeah, sorry. So just in around here. So what's producing that is that O to CH. So that O to CH, that's what's being produced here. So it's very powerful in that I can deduce the functional groups, and I can deduce how many hydrogens are beside the hydrogen environment. It's very, very powerful. So you can see there how, looking at these peaks, the peaks tell you the environment, the delta scale or the chemical shift here will give you an insight, or the figures will tell you which exact functional group it can fall, or you can deduce what kind of functional group that it may be a part of. And yeah, exactly, just it tells you, it kind of gives you a good makeup of the organic compound you're given. So I think that's the last one. It's just another, it's a nice one to look at, that you can apply the data sheet with. Again, remember I mentioned the OH. So OH and NH are tricky in that it can be produced anywhere. So this can, it could turn up in the 9s, whatever, and you know that this is always going to be a singlet as well. And there is an interesting test that's English. There is a test that's done that you can confirm this. Now, you don't need to know it, but it's called a D2O shake. And what this does, if you can imagine a spec, and let's say I'd like a CH2, CH2O. It's terribly drawn, but just give an example here. I'll actually make this. If I used H2O, I get this signal. If I used heavy water, denutriated water, also known as heavy water, again, I'm just replacing the H with deuterium. What this can do is this can confirm that this is a OH group. That's all you need to know, or it's never come up and it's not on the spec, but it's just interesting to know you've got this D2O shake. And when you fire this through a sample of this bad boy over here, it can just confirm that an OH is present. That's all. It gets rid of this little peak here. And when you wash it through D2O, it comes up like this. And that's kind of as much as you need to know about that. You just run it through heavy water and it confirms, when you see this peak is gone, it kind of confirms the presence of OH and NH as well. And that's already there. But that's kind of going beyond the spec a little bit, just in case you wanted to know. The last thing, I think that's all. I think what's important to note as well is we've been going through 3 main types of spec, and that's all you need to know for A level. But it's really important that you appreciate that it's not one spec for one thing or one spec for all. Any lab will go through and use them all together, use them all in conjunction with each other. So they'll do like a coupled spectroscopy, and they can confirm that then with like the NMR spec. So what's good about NMR? NMR can deduce like the presence of functional groups and kind of confirm them as well. Mass spec will actually give you the relative molecular mass, and it can break up the types of fragments that it can be broken up into. And then the NMR as well, it tells you the environments throughout the molecule. So anybody, it's a really good everyday use. So if you thinking of forensics, so if you're trying to tie somebody to a crime scene, you'd always get an expert in that has done the analysis, and in court they'll show all of these 3 results to confirm that such and such was linked to this crime scene because they match up. The molecule that was found was also found here, and this is the molecule. Makes sense. Another way this is used is in sport. So if you wanted to analyze a sample of blood from an athlete that you suspected of using illegal drugs, again, the blood analysis would come up and it would show the exact kind of compound that's in the blood, whether it's illegal or not illegal. Again, you can do that. What else is there? Forensics. I suppose just in general, if you're trying to find an organic compound as a whole, it's just really, really good. I mean, this is what you use all together, very, very powerful to confirm the structure and what kind of exact compound it is. But that's all. Again, any questions, do ask. Don't worry too much about this section at all. I just thought I'd add it in. The important thing is that you can differentiate and really know what the chemical shift tells you, what the integration tells you, and what the splitting pattern tells you. But no, that's all. I hope it kind of helps. Again, do use this to help you consolidate some of the learning. I think the book is a little bit, could be explained better, but that's what you have to work with. But no, thanks very much, guys, and I hope to see you soon.